Okay, so here we are looking at homogeneity with respect to unit. So the first formula we have is weight. So we know weight is mass times gravity. Okay, so I've written out that formula here, weight equal mass times gravity. And what I've done is I've expressed that same formula in terms of a unit. So underneath weight, I've written the unit that weight is measured in, so newtons. Underneath mass, I've written the unit that mass is represented with, so that's kilograms. And gravitational field strength, G, it's represented, it's the same as acceleration due to gravity, which is meters per second squared. Now, that's your standard base unit, and that is in the form, G is also in the form of standard base units, kilograms, meters, and seconds. So what we've got is on the right hand side of this formula, we've expressed it as standard base units. On the left hand side, it's in newtons. However, we've got to show that the units are the same on both sides. So it's not enough leaving it here, saying that the newton is equivalent to kilograms meters per second to the minus 2. What we need to do is we need to make sure that the newton is actually the same as that. So we know that the newton is its force. So force is measured in newtons. So we've got a formula for force, which is mass times acceleration, Newton's second law. So that force, which is newtons, can be expressed as mass, which is kilograms, times by acceleration, which is meters per second squared. So here what we've done is we've looked at the fundamental formula for force, which is F equals ma. We found that the newton is equivalent to that unit, and all we've done is now we've put the newton, express the standard base units here underneath newtons, and we see that the newton is the same as kilograms meters per second squared, which is the same on the right hand side. So the units on both sides are the same, i.e. homogeneous with respect to units, the same on both sides. Okay, now kinetic energy. We know that kinetic energy is half times mass times velocity squared. So we know that kinetic energy is measured in joules. We know that mass, half doesn't have a unit, so there's no unit to express it in. So mass is measured in kilograms. Velocity is measured in meters per second, ms to the minus 1. However, it's squared, so that ms to the minus 1 is all squared. That expanded out is kilograms meters squared seconds to the minus 2. So 1 joule or joule is equivalent to that as a standard base unit, as this is expressed in. So we now know that kinetic energy, in terms of its formula, ends up with base units like that. But we also know that energy transferred from basic principles is work done. So energy transferred, work done, is force times distance. And the joule is equal to, as we previously worked out, that force is kilograms meters per second squared times by meters. So we know that the joule expressed as standard base unit is kilograms meters squared seconds to the minus 2 from its definition. So this is its definition for the joule. So we can see that the joule is represented in this unit. So underneath joule, I've written out the expansion in terms of base units there. We've already expanded that out previously, so that's on the right hand side, and we see that the units are the same on both sides. Now, you could leave it like that in your exam. You don't have to go and write it here, but this is just to confirm that both sides are the same with respect to units. Now, the next is power. So power, electrical power, we know is current times voltage. Current times voltage. Power in units is watts. Current is amps, and we're multiplying it by potential difference, voltage in volts. So watt is the same as current times by volts. Now we know volts is not a standard base unit. We know amps is, so we leave that. We know that the potential difference is the energy per unit charge. So that's energy joules per unit charge that I should have written in coulombs. Okay, so that should not be Q, that should be coulombs, which is C. Okay, spotted my mistake there. So that is joules per coulomb. Again, joules is not a standard unit, a standard base unit. Coulombs is not a standard unit either. So we need to do further expansion here. So joules, as we worked out earlier, it's kilograms meters meter square seconds to the minus 2. So rather than write joules, I've written that there. And because it's divided by charge, we know that charge is equal to current times time. So that is amps times by seconds. And we know that is the base unit representation. Amps is a base unit, seconds is a base unit. So because it's divided by charge, coulombs, so that will be amps to the minus 1 and seconds to the minus 1. Now, if you're not sure of where amps and seconds came from, if you look earlier in part 1, I do expand out potential difference in base units and charge in base units, and you'll see that you will get a representation of voltage and charge. But this is the expansion. So that's your joules, that's your charge, which is per unit charge. So it's divided by amp second. So it's amps to the minus 1, seconds to the minus 1. I'm bringing it all together. You'll see the amps and the amps cancel out. And it's kilograms meters squared, and then seconds to the minus 2, seconds to the minus 1. That ends up as seconds to the minus 3. When we multiply, we add indices. So power is represented as kilograms meters squared seconds to the minus 3 using that formula. However, we also know that the watt is energy divided by time, so joules divided by seconds. So we know joules is kilograms meters squared seconds to the minus 2. We know that that's seconds to the minus 1 times by seconds to the minus 1. So we know that the watt from basic principles is kilograms meters squared seconds to the minus 3. So I'm going to put that in place of the watt. So therefore you'll see that this unit and this unit are exactly the same. And finally, not finally, there are a couple of more questions. Equation of motion, v squared equals u squared plus 2as. That is a formula in kinematics, and you'll see this later on. V squared is velocity squared, u squared is initial velocity squared, and a is acceleration, and s is displacement. So velocity squared, that's meters per second all squared, equals, so that's equals u squared, which is initial velocity squared, so that's still velocity, meters per second all squared, plus that 2 doesn't carry any unit, plus acceleration we know is meters per second squared, plus multiplied by displacement, which we know is meters. Okay, so expanding that out, that gives us meters squared seconds to the minus 2. Expanding this out here gives us meters squared seconds to the minus 2. Expanding this out also gives us meters squared seconds to the minus 2. And then this unit plus this unit, still the same unit. If we add this value to this value, they're the same unit, so we can add them up. So it's the same unit again. Okay, we don't multiply anything out, it's just addition. So we see on the left hand side, on the right hand side, it's the same unit. This is a nice question for homogeneity. Okay, and elastic potential energy, we've got a half times by the force constant times by the extension squared. Elastic potential energy measured in joules. The half doesn't carry any unit. The force constant is Newton per meter. And we've got extension squared, so that's in meters, so meters squared. Now, in newtons, we multiply, so leave that there, meters to the -1, meters squared, they kind of cancel out, and we end up with newtons times by meters. Okay, newtons is not a base unit, so what we're going to do, expand that out. So it's kilograms, meters, seconds to the -2. That's from earlier on for force, mass times acceleration, and then we times it by the mass there, and we end up with kilograms, meters squared, seconds to the -2 by meters times by meters, that's meters squared, and that's there. So a joule, elastic potential energy, so the joule is equivalent to that there, but we need to we need to find out what is the joule. So from basic principles, we know that's work done, force times distance, and expanding it out, that gives us kilograms, meters squared, seconds to the -2. And we'll just put that here, and we find out that's the same on both sides. So the units are homogeneous, the same on both sides.